am excited to be here to share our work on heat transfer and fluid flow in additive manufacturing. Just to be on the same page with everyone, I want to talk a little bit about what I have planned for this talk. Heat transfer and fluid flow, of course, depends specifically on the additive manufacturing technology. So which variants, and then the basic questions of why we need to look at the heat transfer. The simplest and the most elegant of all of these models is heat conduction models, their capabilities and limitations, and then move on to the next topic, which is how convection, particularly flow of liquid metals, affect these simulations, present some selected results, and summarize the main contributions. There are three techniques that I need to focus on: the powder bed fusion, the directed energy deposition, and the gas metal directed energy deposition. The specific attributes of all of these, they are known to this audience, so I would not spend a great deal of time except to point out that the deposition rates vary between the powder bed fusion and the directed energy deposition, the rate being highest for the directed energy deposition and lowest for the powder bed. In terms of the dimensional accuracy and also the surface roughness, we have the best control in the powder bed fusion where the deposition rate is the lowest. And very often the directed energy deposition gas metal arc process requires post-processing and machining for the surface roughness and the dimensions of the product. So why is the heat transfer important? In short, it is necessary for understanding the process as well as the product that we make. If we look at the specifics, thermal cycles at different locations that determine the local microstructures and properties come from heat transfer and fluid flow. The role of different alloy compositions and AM processes also can be understood from simulations of heat and fluid flow. The geometry, composition, and structure of the parts are dependent again on heat transfer and fluid flow, and defects in the parts that we make with additive manufacturing and heat transfer and fluid flow allow us to control those defects. And spatial and temporal variation of cooling rates, this is something that people have been working on for a long time, and we have a greater understanding of these. And this is the driver for the microstructure and properties of materials. Residual stress and distortion is a common difficulty that we have to address, and the starting point here again is heat transfer and fluid flow. If we don't want to do too many trial and error tests because the tests are expensive, one alternative is to augment the experiments with some simulations, and those simulations will always start with heat transfer and fluid flow. Chemical composition change is very often a feature of additive manufacturing because we use very high temperatures, and therefore some of the more volatile alloying elements are lost selectively. As a result, the composition of the final part may be different from the composition of the consumables that we start with. So this is another factor that we can understand using heat transfer and fluid flow. Finally, grain size distribution and topological features are also an important factor. If you take all of these and add them up, we can use a parameter called printability, that is its ability to resist defects and to make sound parts with good microstructures and properties. So the ones that are in red colored items on the left are still developing, and the ones on the right we have a better handle on. Many groups all over the world are working on this, and we have made more progress on understanding of all of these things. So we understand that heat transfer is important. We have an energy source independent of which process we talk about, whether it's PBF, powder bed fusion, or directed energy deposition processes. The material interacts with the heat source, it locally melts, the heat source moves, so there is a temperature gradient. And because of this temperature variation within this fusion zone, a liquid metal flows. It is not a stagnant metal, and also the pool is moving. So there is movement of the heat source, there is heat loss from the sides, and there is heat absorption. So energy supplied by a heat source is absorbed by the feedstock, and then heat is conducted through the part, liquid metal flows, and convection and radiation allows loss of heat from all surfaces of this part. If we focus only on the heat source can be characterized in a general term in terms of this profile on the left. There is a minimum cross-sectional area here that we call beam waste. We have a distribution of power density given by a Gaussian profile that depends on the axial position and also on the radial position. If you look at these three profiles of power density distribution for three different values of this parameter F, that is a distribution parameter, we can have a very sharply focused beam to a not so sharply focused beam and some intermediate focusing that is shown here. So power density distribution is very important because it determines the mode of interaction between the heat source and the material. Specifically, if we were to plot the beam power density as a function of the depth to width ratio of the fusion zone, in this case, we have a very high beam power density, and we have what we call a keyhole mode. That means some of the portions of the metals vaporize instantly, and we form a vapor cavity called keyhole, and the liquid metal starts moving all around the keyhole. Whereas at lower power density, we have a conduction mode typically characterized by a hemispherical fusion zone with no vapor cavity. In the intermediate power density distribution, we can have either conduction or keyhole mode, or in some areas, both. That means we have a very low penetrating keyhole somewhat here, and then we also have a somewhat hemispherical fusion zone. The heat can be absorbed by the powder bed or by the stick electrode or wear electrode that we may use. A simple question: how hot is the molten pool? Of course, it's much hotter than the boiling water or sauna. It's much hotter also than the oven, kitchen oven, or the campfire, or even the lava that comes out of the mountain. So in short, it's somewhere between the lava and the surface of the sun. And in 3D printing, we have temperatures in the range of melting point of the alloy to the boiling point of the alloy. So there is a range of temperatures that we encounter depending on the alloy and the heat source and the process parameters that we use. But in simple terms, we don't know it until we do some calculation. So the easiest calculation is by heat conduction models. And I would like to point out some results from Professor Dey's work. And this is solution of the Fourier equation that is given on top. If you solve these analytically, you can have a temperature distribution in 3 dimensions. If you take a profile of temperature at the solidus and liquidus temperatures, you have a pretty good idea of the dimensions of the fusion zone, and this is what is shown here, analytically calculated dimensions. W is the width of the pool, and D is the depth of the pool, and RB is the radius of the heat source. So D by RB plotted against experimentally measured value of the same quantity. And you can see that using this heat conduction model, it is possible to accurately determine the fusion zone dimensions of depth and width. So it's useful in many cases. And how good are the predictions? One of the ways of checking that out is to compare with experiments. And what you see here are the effects of varying laser powers from 100 watts to 150 watts for a given set of parameters. And the calculations can accurately determine the geometry. It's very elegant, it's very rapid, and it's very reliable. Well, it is reliable under certain conditions. It is very important for all of us that want to use models to understand their limitation. Here, the limitation is this is applicable when heat conduction is the primary mechanism of heat transport within the fusion zone. When convective heat transfer is important, we should not use the heat conduction models because the mechanism of heat transport is different. And there are some other limitations, like if we want to look at the effects of what we call surface active elements, elements that have a large negative enthalpy of segregation, that love to go to the surface and modify the temperature gradient of surface tension. For those elements, the shapes change with small amounts of elements like sulfur, selenium, tellurium, oxygen. And under those conditions, we should not be using heat conduction models. When there is a keyhole, it's difficult to use those models, although approximately they can be used. Cooling rates are often overpredicted. That's another artifact of heat conduction models. And specimen orientation cannot be computed. Like if the surface is tilted, then we cannot use these. So I'm going to talk a little bit about those limitations. Here is a quotation from Benson, Gratoft, and Harry Badeshia on analysis of cooling curves from fusion zone of steel weld deposits. So this is like a single track weld deposit published in Scandinavian Journal of Metallurgy, and it says the heat conduction equation has been found to be inadequate in representing experimental cooling curves. Why does he say that? If you plot the cooling rate from the heat conduction model divided by the experimental cooling rate, you will see that the cooling rate calculated from heat conduction model were about 13 to 18, 19 times larger. So there is a huge error in terms of this ratio. The cooling rate calculated by the heat conduction model can be 18 times larger. So we have to be careful in where we use it. Badeshia and co-workers recommended use of an empirical correlation rather than heat conduction models. And convective heat transfer calculations do not have any such problem. The models that consider convective heat transfer, and this is shown here, this is a V joint, And if you compare that with an L joint, the fusion zone geometry is different. In order to understand the effect of tilt angle, we need to actually consider convective heat transfer. We cannot just use heat conduction models. And also, there is a parameter that we call Peclet number that tells us the heat transported by convection to heat transported by conduction. If this parameter is much larger than 1, then convective heat transfer is the primary mode of heat transport, and there we must use heat convection. Also, the fusion zone is not always hemispherical, and the parameters that determine that are Prandtl number and Marangoni number. Prandtl number is the ratio of viscous diffusion rate to thermal diffusion rate, and its value is from very low to about 10 for different materials. And Marangoni number is a measure of the surface tension force to viscous force. And in simple terms, it tells us the magnitude of the velocity resulting from surface tension gradient. And if this number is very large, then we may not have a hemispherical pool. We can have a bracketed shape pool or a pool that is like a W, depending on the material and process conditions. So heat conduction models cannot determine these types of pools. So we need to do calculations with convective heat transfer. Also, role of surface active elements such as sulfur, selenium, tellurium. Here we are showing for a steel fusion zone, one on the left is 20 parts per million of sulfur, and one on the right is 150 parts per million of sulfur. When we have 150 parts per million of sulfur, the convection pattern is different. And on the right, we have liquid metal, hot liquid metal from the middle of the pool going downwards and melting the pool way below. So we have a deep pool and a narrow pool, whereas if we have very little sulfur, like 20 parts per million of sulfur, we have liquid metal that flows from the middle to the periphery on the surface, and it melts the sides. So we have a wide pool and a shallow pool. In order to appreciate this difference, we cannot just do heat conduction calculations and explain away these types of differences. So there is a place for heat conduction models when we need a rapid calculation and when heat transfer occurs primarily by conduction in very small pools, in many cases in powder bed fusion, but also when we have larger pools, we have to be careful about the mechanism of heat transfer. So what causes convection? There are three main reasons. One is surface tension gradient. The spatial gradient of interfacial tension is a stress known as Marangoni stress, and that can result in a flow that is shown here in a cross section. We also have a current and a voltage in the wire arc additive manufacturing, where the cross product of the current density and the velocity field is the electromagnetic force field, and that can drive a flow as well. And finally, we know that hot liquids rise and cold liquids sink. So gravitational force leads to the convective flow pattern shown on the right. If we look at the relative magnitudes, surface tension force is the dominant force in most cases. And then the buoyancy force is the least important force, and electromagnetic force, depending on the current and voltage, usually lie between these two extremes, the surface tension force and the buoyancy force. Flow of liquid metal affects the geometry, the heating and cooling rates, and the microstructure and properties. So what type of flow do we have? We have a flow that is shown typically here. So the liquid metal is like this little kid cartwheeling within this fusion zone. And if you look at here, it is shown schematically. Normally, the hot liquid will flow outwards and then turn around and go up. Typical velocity is on the order of 50 to 300 centimeters a second. If you compare this with the 100-meter sprint in the Olympics, that's about 10 meters a second. So the velocity here for this cartwheeler is about a meter a second, and this is about 10 meters a second. This is lower than both of those, and you can see the pattern more clearly in this little video. If we have a gas metal arc heat source and we are depositing material by gas metal arc additive manufacturing, then we will have right under the arc a depression in the pool, and the pool will look like this deformed pool. This is because of the arc pressure that depresses the pool and pushes the liquid metal behind. And droplet impingement is another factor that causes higher penetration. So we have a large weld pool here or large fusion zone here, and as a result, we get a very high deposition rate using gas metal arc process. If we have a powder bed fusion, the pool is very small compared to wire arc and compared to DED, and the pool is almost a flat pool. It's a small pool and a flat pool. And intermediate between the powder bed fusion and the wire arc is the directed energy deposition, where the addition of the powder gives us a curved surface on top and fluid flows in all three directions. So we have an intermediate sized pool here, a small pool here, and a large pool in case of the wire arc process. It's more clearly shown about the surface profile of DED GMA, DED laser, and powder bed fusion laser. But the most important thing here are the dimensions. These are not drawn to scale. The dimension of the pool is much larger. Look at this, half width is about 4.1 millimeter, whereas in this particular case, at the lower one, where we are showing powder bed fusion laser, the half width is only about 1/3 of a millimeter. And if you focus on directed energy deposition laser, the pool shape is hemispherical down below, but the size is intermediate between what we get in the powder bed fusion laser, very small pool, to directed energy deposition GMA that has a very large pool and gives us a higher deposition rate. So we can predict the fusion zone geometry using a heat and fluid flow model. And if we look at the thermal cycles at different layers, we can predict those for different conditions of process variables. So if we have concern about overheating and what speed we should go, a few simulations can provide a safe operating parameter. And this is a tool that can be used very easily together with a limited number of experiments to optimize the process variable. Now, how important is fluid flow? It depends on the ratio of heat transfer by convection divided by heat transfer by conduction. If this ratio is small, then I think we can use a very elegant, very rapid calculation of heat conduction equation. But if the value of Peclet number is much larger than 1, then it means that heat transfer by convection is dominating the heat transfer by conduction, and therefore we need to do a more rigorous calculation. So here we are comparing for three different materials, typical working conditions in which we have different velocities calculated by heat and fluid flow model, the length scales, and then the thermal diffusivities. So Peclet number is velocity into length scale by thermal diffusivity. And you can see that for Inconel 625, its value is about 16, 17. And for Ti 64, it's about 9. But one thing is common. In each of these cases, the Peclet number is much higher than 1. So if you want accurate calculations, then it is important to do both heat transfer and fluid flow calculations in order to get the temperature fields, the cooling rates, and other parameters. There are many different heat and fluid flow models. One of the earlier models for the calculation of free surface is called the volume of fluid model. And there are several papers that go back more than 10 years that is capable of tracking the free surface. But these are very computationally intensive calculations. They also are known to be notorious for accumulating errors and in the calculated deposit shape and size. And they often do not agree very well with experiment. The other types of models that are gaining traction is called powder scale model. Here, the time scale and the length scales are small. Time scales are shown here in microsecond, and length scales are of the order of hundreds of microns. You certainly cannot do calculations of part scale using the powder scale models. If we want to know the details like surface roughness or fusion zone shape and size, maybe this is a viable option in limited situations. But otherwise, it is better to do a finite difference method calculations. And the bulk of the results I presented were obtained by doing those. I'm showing some results presented by Dr. Huiliang Wei. You can see that even the powders are resolved here. Spatial resolution and the temporal resolution is very good, but it's very computationally intensive, and we cannot do a part scale calculation. To summarize, applications of heat transfer and fluid flow models are gaining traction in understanding the evolution of microstructure, the solidification structure, whether the grains are columnar or equiaxed, and we can also do calculations in 3 dimensions. We can get cooling rates, temperature fields. We can use the temperature field that we obtain to do other calculations, like use it in a thermomechanical program like Abacus or ANSYS and find the residual stress distribution in a component. Or we can use the calculations of heat and fluid flow to prevent defects like lack of fusion defects, where there is insufficient overlap of the fusion zones. So there are lots of benefits of doing heat and fluid flow calculations. And with modern computers, even the PCs, this can be done relatively easily. And it's very important to understand both the process as well as the product attributes. And analytical heat conduction calculations are very elegant. They provide temperature fields, fusion zone geometry, cooling rates, and solidification parameters. They are simple and insightful and should be used where possible, where the fusion zone size is small, where the Peclet number is low, this is an excellent choice. But heat conduction is not the dominant mechanism of heat transfer in many cases. They cannot resolve the effects of surface active elements, fusion zone geometry that is not hemispherical, and they overpredict cooling rates significantly, not always, but almost always. Convective heat transfer calculations are computationally intensive and overcomes the deficiencies of heat conduction calculations. And they can resolve features in powder scale, calculate free surface profile, and is basis for understanding the AM processes and the microstructural features, defects, and properties of parts.